Recording. So good afternoon, everybody. It is really a pleasure this afternoon to have an informal seminar from Anamaria Gkini. You have seen her around these days. Just a few words of introduction. Anamaria got a physics degree at Stockholm University in Thessaloniki, in Greece, and then for her master's she moved at the Capodistria University of Athens. And since 2021, she's a PhD candidate at Stockholm University, working under the supervision of Ragnhild Blom.
Yes.
Okay. And working on for a PhD thesis on supernovae. Her talk will be today chasing eruptive mass loss prior to superluminous supernova. Okay, so thank you, Anamaria, again.
Yes.
You have 30 minutes.
Yeah.
Give you 5 minutes.
Yeah, okay, great. Thanks, Michele, for insisting to give a seminar today here. So yes, I'm a last year PhD student. I'm finishing my PhD this year, supposedly, and I will present what I have spent most of my time during my PhD, which is about eruptive mass loss in progenitors that explode as superluminous supernova. So I guess that you're not very familiar with this topic. That's why I have put a lot of introduction also for you to understand what exactly I'm doing. And I will start with historical events. So thousands of years ago, astronomers start noticing that there are some new objects that are appearing in the sky, and then after a while they disappear forever. These are some of the historic objects that they have started noticing: supernova 185, the Crab Nebula supernova, Tycho Brahe supernova, and Kepler supernova. And these objects now we know that are supernova, which is the explosions of stars at the end of their lives. But however, back then, of course, they didn't know what exactly was what they were looking at. The way of observing this supernova has changed a lot, especially lately. 100 years ago, or less than 100 years ago, the way of trying to find supernova was by comparing photographs that they were taking. They were taking, let's say, a photo of one part of the sky, then they were taken after months the same photo, and they tried to compare to see if there was a new object appearing in this new image. But as you can understand, this is not very feasible to do it now that we have all this data, because now we have the time domain surveys, which surveys scan the night sky every 3 days, 2 days, depending on which survey we are talking about. And they try to find new transient events, not only supernova, but in general objects that they appear, they are in the sky for a few days, and then they disappear. So the way of trying to identify a transient event is basically these surveys, again, scan the sky, 3 days, they scan the sky again 3 days later, and they subtract these two images in order to see if there is any new spot in the new image. So we have the science image, the reference image, and the difference image. And this is why we want to construct the light curve, which is the evolution of the light of that object with time. The light curve of a transient event has a rise, a peak, and a decline. But this doesn't mean that what we are looking is a supernova. Maybe it's something else. So the way of really classifying an object as a supernova is by taking the spectrum. There are dedicated surveys that they try to classify supernova or in general transient events. And I have put here two, the PESTO and the Bright Transient Survey that I am part of, because I went to observe with these two surveys. And these are two nice photos. One is from La Silla Observatory in Chile, and the other one is from the Palomar Observatory in California, where I went during some observing grounds for these surveys. And now we have more than 60,000 spectroscopically confirmed supernova. Okay, but what is a supernova though? There are two main kinds of supernova: the thermonuclear supernova, or supernova type 1a, in which we have a white dwarf, which is the end product of a low mass star, and is in a binary system. It accretes some material from the companion star, And when it reaches a limit, which is called Chandrasekhar limit, then it explodes. Or we have two white dwarfs in a binary system where they merge and they explode. And then we have the core collapse supernova, which is what I care about. We have a massive star, more than 8, 9, 10 solar masses, depends who you ask. And the stars, while they are in the main sequence, they fuse hydrogen in their core. At some point, they do not have any more hydrogen, so they start fusing heavier elements, helium, carbon, oxygen, neon, magnesium, silicon, until the formation of an iron core. And at the end, let's say that the star looked like this, an onion-like structure, where the core is iron. So in order to fuse iron, it doesn't produce energy, it requires energy. So that's why the iron core collapses. And due to some physics that is happening there that I do not really deal with, the implosion turns into explosion, and this explosion ejects all the outer layers of the ejecta. And there is where the observers seeing the first signal of the supernova, in which, of course, we do not see a star because the star doesn't exist anymore, but we see a compact object, which is a neutron star or a black hole, and the ejecta, which is the outer layers of the star. Of course, life is not that easy, and also the life of the star is not that simple. The star, during its life, can lose a significant amount of mass through a mass loss mechanism. And it can, in some cases, lose completely the hydrogen or even the helium envelope way before it explodes. So again, through the same channel, it explodes, but now, apart from the compact object and the ejecta, we also have a circumstellar material around the supernova, which has been formed by this previously ejected material. There are three main ways of mass loss mechanisms in stars. The stellar winds, where the star loses mass through winds, and this can happen already from the main sequence. A binary interaction, where we have a star in a binary system and it accretes material, or the companion accretes material from the star, so it loses some outer envelopes. And the eruptive mass loss, in which the stars lose significant amount of mass suddenly at the later stage of the stellar evolution. And one very famous way, or model, or theory, as you would prefer to say, is the pulsational pair instability, in which we have a massive star with a helium core of 30 to 65 solar masses. This satisfies the criteria in the core for the pair production, which simply speaking means that it uses some photons that they put the pressure. They uses these photons in order to produce electron-positron pairs. This has as a result the core to contract, and the temperature and density increases, and we have the explosive burning of the silicon and oxygen, which releases energy enough in order to eject the outer layers of the star. And depending on the mass of the star, this can happen multiple times. So what we have at the end, and what we care about, is that we have our supernova, but we have multiple CSM shells created around the supernova, which can be a result of these multiple ejections that happen before the star explodes. So you can imagine that with all these things that are happening before the star explodes, the supernova comes in different flavors. So the main distinguish is if the spectrum has hydrogen or not, if it has its type 2, and depending on how narrow are these hydrogen lines, or broad, or if there are other lines there, they also have some subgroups that I will not talk about this at all, because I care about the type 1, where they do not have hydrogen, which means that they have lost the hydrogen envelope way before they explode. And again, depending on if they have helium or not, there are some subgroups. But today, I will focus in this circle, which is the superluminous supernova. And again, they also come in different subgroups. Type 1b, if they also have helium in their spectra, and type 1c if they do not. And today I will talk for type 1c, which means no hydrogen, no helium. They have completely lost these two layers before they explode. A superluminous supernova is a transient event, which is 100 times approximately more luminous than the normal core collapse supernova. They are very rare, And as you can see here, there are quite differences between the superluminous and the normal supernova. They are brighter than -20 magnitude, and they also have longer time scales, which many times is translated that they have more ejecta because the diffusion time is longer, which could mean that the stars that explode the superluminous supernova are more massive than the one that explode the supernova. And the main problem in the superluminous supernova community is what powers these events, these very bright events. So in typical supernova, what powers the events is the radioactive decay of isotopes nickel-56 and cobalt-56 that they are synthesized during the explosion. And from the peak of the light curve, we can estimate the mass of the nickel. But the peak of the superluminous supernova cannot be explained by the mass of the nickel that we see that is produced, or we estimate that is produced in the supernova. So we have to come up with some alternative mechanism that could power these events. The main four is the pair instability, magnetar, fallback accretion, and interaction with the CSM. The pair instability is pretty similar with what I talked before with the pulsational pair instability, but we encounter this for even more massive stars. And now the energy that is released from this explosive burning, I described before, it's enough to completely disrupt the star. So we have a star that is completely disrupted and there is no remnant, there is nothing, which is good as a theory, but we have never observed it. There are a few candidates, but we cannot exactly be sure if this really exists. Then is the magnetar. Magnetar is a very rapidly spinning neutron star with a high magnetic field. And it's the best model that we use in the superluminous supernova because it's so flexible that it can fit everything without this meaning that the results that we get are feasible. But it's the first one that we usually explore in the community. And it's good because it can explain some things, but it cannot explain some other, of course. Then then is the fallback accretion, where we have the formation of the black hole. We have material accreted into the black hole. This can form some outflows that they can thermalize the ejecta and create this extra energy that we want. And then we have the interaction with the CSM. So we have the ejecta, it crashes into the CSM. This creates shock, which is radiative and also gives this extra energy. Which one is the true scenario that powers our objects? We have no idea. Though we can, there are also the hybrid models, so we can have a combination of these models as well. But one good way of trying to understand what is going on is by looking at the spectrum. So in general, this is a typical spectrum of a superluminous supernova type 1. It has no hydrogen, no helium, as I said before. It has some weak carbon-oxygen lines, and it has a very strong magnesium 2 at 2,800 angstrom. Today, I will focus on the near UV part of the spectrum, which we have the feature, the magnesium 2 from the supernova, which is broad and it has this very characteristic absorption and emission profile. And it has this as well, these two lines, which are magnesium 2 that are coming from the host. However, recently, there were discovered two objects that, apart from the magnesium 2 from the host, there was also another second magnesium 2 system, which was blue shifted by a few thousand kilometers per second. And in one of the papers, it was interpreted as fast-moving material, that it has been ejected around 30 years before the supernova explosion. And motivated by this, we submitted a proposal to get the X-shooter spectra. It's a spectrograph in the VLT ISO of superluminous supernova. And we observed in total 19 objects with redshift more than 0.1. And this cutoff at the redshift is because we want this part of the spectrum to be within the spectrograph. This is only why we have this cutoff. One object was analyzed in my first PhD paper, and I will come back to this at the end of this talk. And the analysis of the whole sample is something that I'm working now. But this talk will be about two objects that we found that they also show this same signature as the two objects I showed before. The 2020 XGA, 2022 XGC. I put these photos because I want to show what we really see when we say we found a supernova. Basically, there was nothing here, and there's a bright spot here. I will not go into the detail, but I will focus mostly in this part that I study, and is the main part of the paper. So these two objects show, apart from the magnesium-2 from the host, also this extra system, blue shifted by around 4,000 kilometers per second, let's say. And in order to derive some properties about these CSM shells, we use Monte Carlo code, which takes as an input the energy of the photons at this part of the spectrum, and it generates synthetic lines. And from the velocities of the lines, we can extract information about the size and the thickness of the CSM shell. So using this code, we model the lines of this magnesium-2, and we found that in one object, the CSM shell was expelled approximately 11 months before the core collapse, and in the other object, 5 months before the core collapse. So in both cases, it was expelled less than a year before the explosion of the supernova. So the very, very, very late stages of the stellar evolution. Since we also have this other object, the 18 IBB, that it was found and we motivated by this, we did the same analysis in order to see if our paper and that paper agrees in the timescales of the ejection. And we found that the CSM shell in that case was ejected around 9 months before the core collapse. But in this case, the CSM, the ejecta, has already interacted with this CSM shell. So we wanted also to do something similar and see if we see any signature of interaction, either in the photometry or in the spectroscopy, that it shows that our ejecta with the CSM has already interacted. In one of the objects, it showed that it would interact around 150 days after the explosion, and we do not have data in this regime. In this object, though, it shows that it would have interacted around peak, which means that the time that we have obtained our spectrum, this ejecta has already interacted with the CSM, but we hadn't seen anything. This is not weird, because in order to see interaction signatures, it really depends on the density of the ejecta and the density of the CSM. But we start seeing a change in the light curve around 100 days, which might mean that we start seeing the effect of the interaction, but of course we didn't get any spectrum at this time. So we have no idea at the end if they interacted or not, or if we are correct or not. Something that is very interesting as well is that all these objects, the 4 objects that show this signature, it's quite different. Some of them are deeper, narrower, broader, which reflects different CSM shells, which reflects different mass loss history for the stars. And one object, the first one that was discovered back in 2016, after 100 days, we do not see absorption anymore, but we start seeing emission, which actually moves from bluer to redder wavelengths. And this is because we start seeing the light echo from the CSM shell. And in different parts, we're mapping different regions of the shell. For example, in the beginning, we see in the front, and then as the time passes, we start seeing the back of the shell. And this can reveal information about the geometry, which was found to be spherical. But of course, we do not have data for our object, so we don't know what is the geometry of the shells. But what the observers do always is speculate. We can start searching what could possibly happen in these cases. So as I mentioned before, the pulsational pair instability scenario, I will mention it also now, because in order to form CSM shells that are dense, and in these distances, you need an eruptive mass loss mechanism. And one of these is the pulsational pair instability. So a search into the models of PPI, it showed that we actually can form CSM shells with these velocities and these distances, and the progenitor stars are around 46 to 50 solar masses, which is quite massive stars. And the geometry could reveal a possible hint of the expelling mechanism, but we don't have, unfortunately, information about the geometry. Something else that we wanted to see is what powers these very bright objects. And we start, of course, with the magnetar. We model our light curves with the magnetar scenario, and we found magnetar mechanism, and we found that it's actually quite good fit, but it gives an ejecta of around 10 solar masses. But before I talk about the star of 50 solar masses and an eject of 10 solar masses, so there are 40 solar masses missing. So what happened to this one? And also how a star that is 50, more than 50 solar mass of solar mass can collapse and explode. So that's why we start also exploring the fallback accretion, in which basically we have the formation of a black hole and we have a material that is accreting, and maybe we have some weak supernova explosion that could possibly explain these 10 solar masses of ejecta. But there are not good fallback accretion models in the community. And what we get is, in order to power these objects, we need 500 solar masses of ejecta, which is not possible, of course. So we need better models in order to see what is going on. Now I will come back to my first paper, in which I wrote this paper because we found some very interesting carbon lines in the spectra of this object that we usually do not see. And we interpreted this as a carbon-rich CSM, that it was actually attached to the ejecta. But later on, these carbon lines disappeared, and we start seeing hydrogen line, which we also interpreted as the ejecta then start expanding and they interacting with the hydrogen-rich material. So in these objects, we know that we have a CSM shell around the supernova, but we didn't see the same light in the spectrum. And this is how the paper that I'm working on now was motivated. So we want basically to study all the superluminous supernova we have collected with our sample, and all the superluminous supernova that they have extra spectrum in the literature, use the code and put some constraints in the CSM properties, and put upper limits in mass loss rates of stars that they explode as superluminous supernova. This is still work in progress, so I had nothing to show. What I will show, though, is this plot, which is not very pretty, but it's okay, which basically shows if a comparison of the peak magnitudes of the sample that we trigger in green, if you can see, and the ZTF sample of superluminous supernova in blue. So we want to see if we were biased on which objects we triggered, but we were not, because we triggered objects that they span across the whole distribution. And the lower panel shows in blue the ZTF sample, a big sample of superluminous supernova. The pink one is the non-detections, objects that we observed, but we did not detect these magnesium-2 lines. And the purple one is objects that we detect these magnesium-2 lines. And the first, what we see here, is that these objects are very bright, brighter than the non-detections and the ZTF sample. Of course, it's not that simple, because if we want to include statistics, we have to take into account also the signal to noise of the spectra and everything. But it's a first result. Yes. So, takeaway messages. The two objects that I study in the paper I presented here, they show these magnesium-2 absorption lines that is coming from CSM cell, which is located around the supernova. These cells were expelled less than a year before the explosion. And in 2022 XGC, we estimated that they probably have interacted, the ejecta, with the CSM. There are only 4 objects that they show this spectroscopic feature. It could be result of pulsational pair instability because it agrees well with the models of PPI. These objects are very important because they show what the star do right before they explode, and they can help us in constraints mass loss rates in massive stars. And the analysis of the whole Exeter sample is what I'm working on now. That's it. Thanks.
So let's thank Anna
Anna.
for the time. I also want to thank Anna because we asked her to give a broad overview of the documents we have from the PCPO so that they know what is at least the peak environment we're talking about.
Did you understand?
Thank you guys for staying and the questions.
Yes.
So I did not fully understand the problem with the 50 solar masses model.
Yeah, the magnetar, you mean?
Yes, I mean the magnet. Because you put that this is the mass of helium core
Yes. So the star is even more massive.
at the beginning.
Yes.
So you cannot exclude some mass ejection before.
Yes.
So the shell around the exploding object in principle could be the imprinting of the previous mass loss episode.
Yes. But we.
So sorry,
No.
why you cannot you exclude the possibility that there is a magnet accreting 10 solar masses to trigger successive?
No, we do not exclude this, but there are
It
not.
seems unrealistic, sorry.
Yeah, but there are not good models that could actually show how the light curve would be if we had a magnetar accreting mass around and thermalize the ejecta.
It is our ability to model.
Yes, exactly.
But in principle, it is possible.
Yeah.
And also the number are fully consistent, more or less.
I don't know if the numbers are consistent because if we have a helium core of 50 solar mass, I mean, when it exploded, it would be, I don't know, 40, 35. There's still a big gap in solar masses that we need to explain. And I don't know how much mass it could be accreted on a magnetar and how the magnetar would be preserved without collapsing.
I am not understanding this issue. What is the problem? This is the estimated mass of the helium core at the explosion?
Yes, at the edge of the explosion, yeah. It's here. What is it? So here. So basically, this there are two different things. This is the modeling in the light curve, which shows, yes, the results from the modeling. And the other is what we estimated based on the distance and the velocity of the CSM shell. So we have two completely different things that we try to match together. So one show, yes, that we are talking about a star of helium core of 45, 50 solar mass, depending if you take into account metallicity rotation. And on the other side, we have something that at explosion should be around, if we say 7, 9 plus 2, 3, 10, 12 solar masses. So unless,
Okay, now I understand. Okay.
yeah, because I mean,
The
this
problem is
plus,
10 against 50.
yes, yes. So there is a big gap that where
At
did
the
it go?
beginning, I was imagining that 10 was the mass of the matter falling on the magnet.
No, this is the mass that exploded. Yes, it was
The
ejected.
ejecta.
Yes, the ejecta. Yes.
Are these models made with MOSFET?
It's a redback. It's a new tool developed by a colleague in our department.
Just two strange things. One is the unit of the y-axis, and I never saw.
The flags.
But the other is the phase. So
Yes.
don't have a well-constrained explosion epoch, or it's just a choice?
No, no, we don't have, but we can estimate it based on the upper limits, because we have the upper limit. So basically, we fit a line, we fit the slope.
Everyone
and
has it. No, but because in my experience with MOSFET parts,
Yeah.
the explosion epoch makes a lot of difference.
So this, This is very important actually, because we use the explosion time in order to derive when these shells were ejected. But the thing is that we have very good baseline. So it should be plus minus a few days. That doesn't make that much of a difference in our estimation. That was also one of the questions of the study.
You had a volumetric light curve.
No, I didn't have the volumetric light curve.
I saw an object in one of the first, maybe 14.
Here? No. Volumetric light?
One of the first slides that you showed.
Ah, here. No, in the introduction.
Yeah,
The?
yeah,
Here?
yes.
Ah, okay.
This is
That's a
a-
random
Okay,
superluminous.
but
Yeah.
the luminosity is very high.
Yes.
Right? So here you could say interaction plays the role. But 10 to the 54 per second.
So
Is
this,
it error per second?
it's yes, per second. In general, this is what we observe in supernova, and this is why the power mechanism is still an open question in the field. CSM interaction can power, but we need basically to convert all this kinetic energy to radiation, and it's not straightforward. And CSM, don't get me wrong, I'm pretty sure that CSM plays a very important role in powering this, because we're talking about massive stars, they lose mass, there is something around the supernova which they eject and interact with, but I don't know if it's the main mechanism.
The thing is, if you have interaction there, you should see in the spectrum. You should see it in the spectrum.
Yeah, yes.
The fact that you see absorption features, it's tricky, because if you see absorption feature, means that the photosphere is well beyond the radius at which the form is.
Yes.
So there must be something deeper inside. So what you are looking at is not the shocked regions, because otherwise you would not see the absorption.
Yeah.
So the fact that you see absorptions.
So we see absorption is because we see, so okay, let's visualize this. We have the supernova, you're the observer. We have the supernova here, ejecta. We have the ISM, which we mostly see magnesium-2 from the ISM. And we see something that it's moving at around 4,000 kilometers per second, which is not ISM, but it's not supernova either.
It's blue shifted.
And it's blue shifted. So it's coming towards you. So this is why we say it's CSM, but it's ISM, CSM, supernova. So it hasn't interacted yet. It's photoionized by the supernova. It's not, we do not really see something from inside the star, from the magnesium.
You don't even see the shocked regions. That's the problem.
Yeah, but no, you're talking about this.
No, this is just an example because it's very bright.
Yeah, no, we do not see, but that's why we say that they have not interacted, because we don't see anything, we don't see emission from this CSM. Like in 2Ns, for example, where we see this narrow hydrogen. Yes, but we do not.
Very complex spot.
Yes,
To visualize.
yes.
Geometry.
I mean, what is really the geometry for supernova, though?
That's,
I have a question. Very nice talk. I have a question. You have before talking about the possibility. You are looking for the possibility of interaction between the shell and the jet. I have not fully understood what is the feature that you use for identifying this, because you have shown some change in the expected behavior of the light curve.
Yes.
You say maybe this is a signature of interaction, but we are not sure. So what is it? A spectral signature or is it photometric signature?
So we do not see anything spectral signature. But as I said before, this is not very weird necessarily, because if it has just the time that we get the spectrum, we estimated that it has interacted or started interacting at the signature. But in order to see the signature in the spectrum, you really need a dense material to crash into a dense material. If the outer part of the ejecta and the inner part of the CSM are not very dense, I mean, these are all speculation, we do not really know what's going on, then it's not unsurprising that we do not see at that particular moment, the interaction. But we see that some days later, we start seeing a change in the light here, which means that there is something that puts extra energy. And that's why we think that maybe we start seeing the CSL interaction, but we don't have spectra to confirm
The
this.
other question is, there is any reliable estimation about the initial velocity of the emission of this shed? What is the initial velocity of this shed when they leave the...
The initial, like when
Yeah,
it was ejected?
Exactly, because I think that the estimation of mass loss, of the rate of mass loss, depends on the velocity of this.
Yeah.
You have
So-
some indication, maybe instead of the final velocity, the one that you are measuring from
Yes,
the spectrum, but
yeah.
it depends also on the initial velocity.
Yeah,
That can come, I think, only from model. There is no possibility from observation.
no, because in order to get this means that you need to get the spectrum exactly when it was ejected, that it's not possible. But so actually 89 dB, this object here, it shows this picture for around 60 days and it doesn't change velocity at all. It's in the same velocity. So we assume that the initial velocity was the same. I mean, we made many assumptions in order to derive this, which could make the difference, I agree. But whichever difference it makes, the most important part is that we have something that had been injected right before it explodes. If it's 9, 10, 11, 15 months, doesn't make that much of a difference. This is where we rely on, basically.
And the last portion of the line curve, this superluminous, is different than the normal one.
It's
Because you have shown the
long.
plot at the beginning
Yeah,
is longer.
it's longer.
But after, okay, it's longer.
It's longer because we estimate that the diffusion is longer, so we have more ejecta, so more massive stars. But this doesn't mean that a massive star that explodes is a superluminous supernova. I mean, we don't have a clue. We don't know this.
I don't know if there are questions online. I have one.
Yes.
You said these are quite rare events,
Yes.
but what do we know in terms of their host environment? I mean, your sample is relatively nearby, it's not too far. But what do we know, in terms of the environment, the galaxy, host galaxies?
So for the host so the thing is that these are objects that are further. Okay, I don't know to which redshift you are working with, but for us it's further, like 0.4, 0.3. This is what I mean. And we usually find them in low metallicity, low luminosity, basically dwarf galaxies, and star-forming regions. So makes sense to be massive stars, but low metallicity as well. This is what we have found, at least in objects, because usually when we study supernova, we also try to understand what is going on with the host galaxy, but we don't get the spectrum of the host galaxy because we cannot. At these redshifts, at least with our surveys and the spectrographs that we have, the surveys usually, we see the galaxy because there was a supernova went off, that there was.
Okay, I remember that.
So we have no clue about what is going on with the galaxy. We try to derive everything from the supernova spectrum, where sometimes we see galactic lines. This is what we do with the host galaxies.
There's no close example that we know what's happening.
There are
The closest we know
is 0.02, 0.0.
is about 100 million watts.
Yeah.
It's, well, which is not too far. So
No, it's, I mean, we see the galaxy well enough, but we still haven't gotten a spectrum of the galaxy. We still see basically, we map the region where the supernova was exploding. This is what, because we care about this particular star-forming region in order to derive properties for the progenitor, but that's it.
okay.
Sorry, but do you think that the association with the low metallicity population is a selection effect or is it intrinsic? Sway all along the
So could be intrinsic. because, for example, in I don't know what to say. Let's say in stability supernova, we are talking about very, 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 very massive stars, which could also, yes, or in the magnetar. So the important thing in the magnetar is we want it to be highly rotating. So if it's metal rich, this the removal of material could take the rotation down, for example. There must be something with the metallicity, but there are also, it really depends on which scenario you assume for the.
Also, the observational bias is very difficult because they are near, if I have understood, so you have no acceleration.
We also
they look at everything. So
very stability are related to.
Low metallicity. Yeah.
Also, when you talk about low metallicity, what is the metallicity?
0 point, let's say, yeah, it's subsolar, yes.
Okay.
Yes,
So-
it's subsolar, yes. 0.3 times the solar metallicity, something like this.
Usually it's a normal.
Yeah.
Start. It was the idea.
Okay, so if there are no more questions, let's thank again Anamaria.
Thank you.
And next talk is next Thursday by Gutierrez will be here in person. Talking again also.
Yes. Okay, she doesn't exactly do this,
Yeah.
but it's similar.
The broad
It's
topic is
supernova.
supernova.
Yes, exactly. Yes.
Okay. Ciao, thank you.
Thanks. I still share. Let